Welcome back to the second half of section 1.3. We're going to look at a few other good methods of sampling. They all have some element of random, but they're a little bit different than simple random sampling. And so that's because sometimes simple random sampling is too difficult or too expensive to obtain. Too time consuming. We'll talk about that as we do examples. And then there's also sometimes researchers are not willing to leave some parts up to chance. And so all of these will be addressed as we look at the three other methods. So we're going to start with systematic random sampling. And this is where you choose things that are equally spaced throughout your population. It's still random, but rather than having a random number generator where you could have a number 1, 2, 10, 20, right? They're spaced, they're just random numbers. We just have like every fifth item, every fifth person in line. So if people are in line, we just pick every fifth person. We could look at an assembly line and grab an item every 10 minutes. So that's equally spaced because it's every 10 minutes. And so because things close together can be similar, this can help avoid a biased sample. So let's do an example of systematic. So we have 20 basketball players and we have their jersey numbers. So this is my data for their jersey numbers. And I want to, instead of randomly choosing 5 players, I'm going to use systematic random. So I need to pick 5 people. So since I have 20 in my data set and I need 5, I divide and get 4. So I think I'm going to lean towards choosing every 4th player. And then to make it a little bit element of random, what I'm going to do is I'm going to randomly choose the first number. So I want the first number to be one of the first 4, and then because of the every 4th player. So should I start with the first person, second person, third person? I don't want to start with the 5th, 6th, 7th person because then I've like left off the first group. So we want to pick one of the first 4 players for every 4th. If we did every 5th person, it would be one of the first 5. So I'm going to go back to that random number generator that we were using, and I'm just going to randomly pick a number between 1 and 4. So I'm going to start with the 4th person. We don't have to start with the 4th person. Let's say you're doing it at home and you get 4 again. Okay, why am I getting 4? I'm getting a lot of 4s. Apparently it's just random. Or you could get the first person, right? So do this at home and see what you get. I just get a random number every time. And this is my starting point. So depending what you get, that's your starting point. So I'm going to clear this and just do it one more time, just because I typed it so many times. So we're going to do 1 through 4, and then this time is going to be officially where I start. Okay, so this means I'm going to start with the 3rd person. If you got something different at home, you could do that as well. They'll both be considered systematic random samples. And remember, every sample is a little different. So we're going to start with the 3rd player. And we got that from random integer. Again, you may have gotten a different number, but I got 3. So that's my 3rd player, and then I'm just going to count. 1, 2, 3, 4, every 4th. 1, 2, 3, 4, every 4th. We're still doing every 4th. 3 was just my starting point. And that way we'll get it equally spaced throughout the whole sample. 1, 2, 3, 4, 1, 2, 3, 4. And we should have 5 players. And so that's my systematic random sample. So I'm getting a little bit of everywhere in the list. It's equally spaced, but we all might have a different starting point, so we all might have a slightly different sample. Okay, so hopefully that helps visualize systematic, like the equally spacing, right? All the numbers are equally spaced. I have 2 more good methods. So let's, if you're ready, we're going to keep going. Cluster sampling is the next one. It's where things are already naturally grouped together. So we're going to identify the subgroups, which we call clusters. These are things that are naturally grouped together. So if I were selecting students, classes would be an easy example. Like you guys are naturally grouped together in a class. It's really hard to select an individual student. It's really hard to like catch you guys to do surveys. But if I caught you all in a class, in that cluster, it'd be easier to make you do a survey. And then as long as we randomly choose those classes or those clusters, it's fine. So we're not going to choose a single class. We would randomly choose multiple classes. And this is just one example. We'll see a different one below. And then we just combine all those classes or clusters to make a sample. And this can save a lot of time. Like grabbing individual students would take forever, but grabbing you guys in a class is a little bit more efficient. The only downside is clusters can have like members and thus increasing the chance of a biased sample. But hopefully if we randomly choose enough classes, that should take care of that issue. So a single class would likely be more biased than if we had like 10 or 20 classes. So here's another example. If you think about grapes, that's another example of things naturally grouped together in their little bunch of grapes, right? They're already naturally grouped. There's my picture of grapes. And so rather than selecting 1,000 individual grapes, that could take a very, very long time. This winemaker has decided to save time, he's going to grab bunches of grapes. So he's not going to grab a single bunch, that would not be good. But as long as he gets enough bunches, it should be okay. So the bunches of grapes are my cluster. And so if you're visual, right, they're naturally grouped together. How many clusters? So one cluster would only give me 40 grapes. 2 clusters would give me 80 grapes, but we need 1,000. So if we do 1,000 divided by 40, it looks like 25 clusters is good, or 25 bunches of grapes. And again, as long as there is some element of random, this will be okay. So as long as he randomly chooses the 25 clusters, or bunches of grapes, then it's still a good method. So he can't just pick the first 25 he sees or the first 25 he likes. Maybe he assigns them a random number and then chooses 25. So it is using some element of random. If they're not randomly chosen, then this is no longer a good method. So if you're ready, I have one more good method. And it's called stratified. We just did systematic a moment ago. Stratified. Stratified sampling is one where we choose different subpopulations. So I think of these as like mini samples. It's a little different. It's not like choosing students in a class and then randomly choosing another class and another class. It's where maybe I'm interested in the age groups. So which we'll see in a moment. Or maybe I want to find students on major. So I would divide you guys by major. So like little subpopulations, we'd have mini samples based on different majors. Hold on till the example and I think it should clarify. But we choose them so that they make up the same proportion as they do in the population. So first we have to identify what our important subpopulations are. And then from each subpopulation, we will get a size proportional. So again, just wait for the example. I think it clarifies it all. And then as long as we randomly choose from these little mini groups or mini samples, then it's okay, right? Everything has some element of random. And then we just combine them to make a sample. So this is helpful when you have an important characteristic that you want represented. The most common reason someone would use this is because we want to study the individual groups also. So my example is we're looking at Chabot, and we want to stratify based on age, which means our little mini populations or our mini subpopulations are age. So it means we're going to have like groups for each age. We'll randomly select, and then we combine them to make a sample. So I don't want to randomly select students. I want to randomly select from 19 or younger. I want to randomly select from 20 to 24, randomly select from 25 to 29, randomly select from the 30s, randomly select from the 40s, and then combine them and make a sample. And so my sample should have 280. I'm not going to divide that by 5 and give them each the same number of students. I'm going to give each group a proportional number of students. So for 19 or younger, we're not going to have 280 students. 31% of my sample should be 19 or younger. So 31% of 280. If you don't remember your percents, you're going to do 0.31 times 280. And we get 86.8, so I'm going to say about 87, because we can only have whole numbers of students. And as long as I randomly select 87 19 or younger students, this method's good. So this might be someone who's studying students at Chabot, but then also wants to study the different age groups. So we randomly select each age group, and then we'll combine them to have a sample of 280. So if you feel like you can do this, you should pause the video and try it. So I'll do the 20 to 24-year-olds. That should be 29% of 280. They're 29% of Chabot. They should also be 29% of my sample. So 0.29 times 280. I think I'm going to set them all up and then pull the calculator out. For my 25 to 29, it's 13% of Chabot. So 13% of the 280, that's what proportional means. Convert to a decimal and multiply. So again, if you feel confident, pause and give this a try. It's good practice. 30s is 15%. So we convert to a decimal and multiply, and then do the same thing for 40s, and then pull out your calculator if you haven't. 40 or over was 12% of 280. So 0.12 times 280. So 40 and older is 12% of Chabot, so I want them to also be 12% of my sample. So I'm going to go ahead and start multiplying, and then we'll check that we have 280 students in our sample. So for my 20 to 24, I should have 81. I'm going to round down. For my next group, 25 to 29, we should have 36.4. Again, a decimal doesn't make sense, so we'll do 36 following rounding rules. These are whole people, which is why decimals don't make sense. No need to round on this group. We get 42, and for the last group, we get 33.6, which all follow rounding rules and round up, so 34. And so I'm going to randomly choose 87, 19 or younger. I'm going to randomly choose 81, 20 to 24. I'm going to randomly choose 36, 25 to 29-year-olds. Randomly choose 42 in the 30s. And randomly choose 34 in the 40 and older group. And that's because maybe this like subpopulation, these little subgroups, are interesting to me as well. And then let's just confirm that these add up to 280, just to check our work. Because our whole sample, when we combine them, should still be 280. Cool, and we got 280. So just good ways to check your work. So we still have a sample of 280 students. We just made sure our age was properly represented. So if you need a little bit more time to calculate and just check that you can do these calculations, pause the video. We just have one last quick example in this section. So our last example is just looking at a student survey at Chabot and kind of figuring out what methods. They're actually using two different methods in this survey. And some of you may have done this survey. They do it every couple years at Chabot. So your class may have been picked before. So we decided at Chabot that it's simple random sampling is just not practical. We're trying to get this survey out to all the students and like trying to find you guys to get you to come in and take a survey, randomly select students and get you to still come in, right? It's 30 minutes. Most of you are not going to come in. So instead we decide to choose whole classes of students, and then your instructor kind of just makes you take the survey because you're already there. So that whole class kind of reminds me of you guys already naturally being grouped together. What do you think? Right, already naturally grouped together. Any ideas what method that is? So that would be cluster sampling, right? The class equals a cluster. So one of the methods being used is cluster sampling. We're not going to choose a single class. because that would be biased. We're gonna get lots and lots of classes. And so the way we tried to get a good mixture of classes, I thought I fixed this typo, but I didn't. I'll fix it on your copy. A good mixture of students from classes of various subjects. They chose classes that were equally spaced through the classes of classes. So imagine you're looking through the schedule and they choose every like 10th class or every, I don't know, 5th class. I don't know. We don't know how many, but we know that it's equally spaced. So thinking back to what we just went over, anybody remember what method was equally spaced? So look back, and if you look back, that's the systematic sampling. So it's a combination of both. So it's okay to use 2 methods as long as it's 2 good methods. This is not stratified. Classes are not stratified students. Classes are just students naturally grouped together. To make this stratified, we'd have to have like a subgroup, like age or major or something. So stratified is a little bit different. But hopefully this gives us a little bit of understanding of good methods. Next, we'll jump into 1.4, and that'll be bad methods, methods you should not be doing to collect data. So I'll see you back for section 1.4.